let's see. It's really truly a great pleasure to be here at Michigan, and not just because the colors are the same, so especially in football season, you know, you're safe wearing blue and maize and gold, maize and blue, sorry, maize and blue, is that what we should say? I have to say, okay, I'm really going to speak, but you know, at Berkeley we do blue and gold, but the gold doesn't print well, so we make it orange, you know. It's maize, I think, is a far better, more photogenic color. It's really a great honor to be here, and you know, a lot of what I'm going to say really exemplifies a lot of what I saw in the ethos of the mechanical engineering department today. So I was really fantastically touched by seeing the spirit of technology to serve society, and I really think it's a fitting theme for the talk today. And the other thing I wanted to say is, you know, it's just wonderful that you have such lectures endowed by distinguished alumni. And just on a personal note, you know, a predecessor of mine as dean 3-4 ago, Dean Ernie Koo, is an alumnus of Michigan. And then, of course, none of his degrees were from Berkeley. But then I remember, is coming to me and saying, I'd like to endow a lecturership, and I'm going to do exactly the same at Michigan and Berkeley. And really, he also felt that it was important to bring leaders, a little more industry-focused leaders to really talk about, you know, the role of technology and changing society. So let me also say that, you know, especially to my friends in control, who it's just wonderful to see after some time, you know, I won't give away technical talk. I really want to, but there'll be a few equations nonetheless, so but just a few. Let me tell you that I think we're at a time where engineering is really poised to make a big difference in how we live and what we do. And let me just lead you through this. I actually think that the opportunities really abound. The opportunities to, you know, it's somewhat trite to just say we do multidisciplinary work. I really think that not only is it multidisciplinary, but, you know, what's different perhaps is that we in engineering now are reaching out pretty deeply into the arts and humanities and social sciences, in addition, of course, to traditional outreach into the physical sciences and the social sciences. And I have to say, because of visionary leadership here at the University of Michigan, you know, you have arts and performing arts and humanities really embedded in the engineering campus. You know, the having put that there is really just a remarkable foresight. So I'll end by showing you some of why this is getting to be so important. I think that the vision really of an engineering education, even exemplified, and I say ours, I don't mean Berkeley, I don't mean Michigan, it's ours as a sort of a group of, as an engineering society, technologists in the broadest sense, really are to solve big open problems, perhaps you can call them grand challenge problems, alleviating poverty, you know, better delivery of healthcare, those kinds of things using today's best technologies. And here are a few. You know, I'm especially interested in how we're going to change infrastructures. Certainly transportation is a big infrastructure here, but all kinds of other infrastructures as well through the new technologies. And certainly energy and the environment, and of course, the delivery of healthcare. Let me start by leading you through one story. The first story is about 2001, 1990 or 2000. You know, everybody started talking about smart dust, which is small sensors which could be used to instrument the environment. And these are some pictures really from an earlier era, you could say, where people wanted to have radios and sensors put together on small, you know, on small devices. And that, I think, has, of course, trucked along. There's been a lot of progress. You know, that agenda, the technology part of that agenda is certainly not done. We are still thinking about really having them deeply embedded inside skins and interactive surfaces, smart objects. But I do think that there's another leap that's needed to make these things super, super small. But along the way, what has happened because of these devices is to really build an ecosystem where you have a swarm of sensors on the outside and the cloud computing on the inside, and the two are intermediated by mobile devices. And that fusion, I think, is resulting in a big change in how we think about the world. And that is exemplified, and this goes under the title of something called cyber physical systems. It's a cyber heart for physical systems. It's certainly an agenda that has been recognized by major federal agencies, certainly the National Science Foundation, and one of your own, Don Tilbury, is out there pushing the cyber physical systems agenda. This is a picture of how the cyber physical systems agenda really is a way of thinking about how we rethink our physical infrastructures with the cyber heart built in. And the cyber heart has, on the one hand, these devices, and quite often we refer to them as the Internet of Things. That's what has become of these little sensor webs. And on the other hand, cloud computing, to be able to do a lot of fast computation and intelligence. And we have certainly a lot of technical challenge problems here. And those problems associated with proving that they're safe, bringing autonomy, real time, human in the loop, privacy. And I'll touch upon some of these technical challenges as we go. But I think that they are changing our society in a completely non-trivial fashion. So that, in some ways, is really the theme of my talk. It's a lot of people are using these terms, which are related. Some that you may have heard are, so the Germans use the term Industry 4.0. And this is a picture of what they might mean by Industry 4.0. I won't lead you through all of this. It really began by Germany thinking about how to rethink manufacturing and especially automotive manufacturing. Mark, we have representatives from GM here, Mark is the executive from GM. But certainly it goes beyond that. And other consortia, so GE launched a consortium called the Industrial Internet Consortium. Microsoft and Cisco and gang were not to be outdone by this, so they announced a consortium called FOG. Another group is sort of swarms, and they all are this notion that you can instrument the world with swarms of IoT sensors, and you extract value from drawing information from them, computing in the cloud, and sending back decisions outside. And those are, I think, all versions of this, and they're making varied kinds of progress. But this particular way of thinking about this, and I'll call it cyber-physical, it's a little bit our US terminology. It's not a term, it's a slightly geeky sounding term. It doesn't roll off the tongue, but I think we're stuck with it for a variety of reasons. Even the Europeans have now adapted it, so they use this too. But what this does is it's been creating a huge number of changes. And some examples are certainly in energy, demand response systems in energy. The whole thing about the entire thing that we refer to as the sharing economy, be it Airbnb, be it Uber, Lyft, all of those kinds of things, and I'll have a few more examples that follow, are examples that come from this idea of working on these data, on the large sources of data from these multiple sensors, and coming up with solutions which are new business models. The future of mobility looks very different, partly because certainly of autonomous cars and so on and so forth, but also ride sharing. Questions about ownership. Is mobility going to be a service? Is mobility a right? And in some circles, you shouldn't be, because you're incapacitated in some way, you should still be mobile. In fact, I think we can all agree that mobility is a very important part of a happy life. So really how we think about all of these changes. In California, of course, water is a perennial issue, as you've seen even in the fires burning today, how you do smart agriculture. And amazingly, we talk about these are not just urban infrastructures. In fact, in the United States, rural communities, farming communities, are far more likely to adopt these changes than the urban communities. So for instance, in farms, it's really, nobody would bat an eyelid about sitting in your porch and driving your combine remotely. And if you look at Caterpillar ads or any of those ads, the notion of having multiple sensors tell you where to irrigate, how to irrigate, where to sow, all of that, this may well be the places where the changes come first. Let me now lead you into a little bit about where I think this digital transformation is coming from. You've seen a lot of these devices. This is Tom Siebel, Siebel Software Systems, and we decided that we want to write a paper for the trade journals. So we wrote this for the McKinsey Quarterly. This is a McKinsey consulting company quarterly about what's driving this. So lots of estimates. Certainly we went through a lot, but then when you sort of go through some of them, the number of internet devices, and this is not a McKinsey, this is say Boston Consulting Group set of pictures saying that the number of IoT devices is growing exponentially. The predictions are 75 billion IoT devices by 2025. Everybody is in this 50 to 100 billion devices range in these forecasts. On the other hand, the cost of computing is dropping at this precipitous rate. This is a log scale, by the way, in terms of what it costs and the year. So the cost of the devices themselves is dropping. Now, this is a little bit more controversial about who's spending. This is a Boston Consulting Group idea about what's being spent by sector on Internet of Things. And I think, again, there is some room for questioning these numbers. You've all had Gartner estimates that we're worried about. But I think we chose an estimate that was the middle of the range. It was lower than the McKinsey estimate. It was higher than some of the other estimates, Cambridge Analytics Associates. It's, the composite spending is really likely to be $100+ billion. And you just take a look at where the biggest spending is on the top. It's discrete manufacturing, logistics, transportation and logistics, utilities, and then, of course, healthcare is a little bit the laggard, but I do think it's likely to pick up in the years to come. An example is this power grid. So the National Academy of Engineering said it was the greatest engineering feat of the 20th century. It's, there's this journal which did it, but we are seeing that the big 21st century piece of this is the sensoring, the IoT sensoring of the electrical utility value chain for condition-based maintenance, for demand response, for dispatching when you send trucks, after a hurricane, after a fire, in terms of where you send people to put in the trucks. And that, when you take a look at it, it's a lot of things. It ain't just big data. It isn't just IoT. It is some wonderful fusion of all of those. And I want to lead you through what that fusion is. And the biggest single thing to think about conceptually is that there's an emergence in the so-called sharing economy of data as a commodity. So you have infrastructures, and there are users generating different kinds of data. Then you have people who are the aggregators. This is Waze, that is C3, is Tom Siebel's current company. It produces a cyber-physical platform for aggregators. There are other examples. And then they offer up the computations done in the cloud, on Amazon Web Services or the Google Cloud or Microsoft Cloud, whichever is your favorite cloud, or maybe on your personal cloud, and then provide solutions to the infrastructure. And so this data is now a commodity. And it's a very different model behind what you used to do, where you just have predictions once a year of what utility people were consuming in terms of power or in terms of road. And so let me lead you through what that does. So it has the promise of improving operational efficiency by being able to model the user. So what does modeling the user mean? Modeling the user means understanding what you want to do with a shared resource. This is traditionally the domain of behavioral economics. By the way, it's not an accident that the last 3 years' econ Nobel Prizes have all been in behavioral economics. And I'm going to say something to this Mechie audience because we kept thinking about mechanism design. And mechanism design in a Mechie department means how you build mechanisms. The things that the Nobel Prizes have been for are also called mechanism design, but that mechanism design is how you design auction schemes, pricing schemes, other kinds of schemes from understanding user preferences to be able to offer services. And by the way, in an econ department, that's what they understand by mechanism design. And that's what the Nobel Prizes have been for. And if you take a look at a company like Google, Google is an ad company. It really is, based on a clever mechanism design for pricing, pricing the ads. And so here, in this case, I'm going to talk about two examples, energy and transportation. What you mean by modeling user preferences is to try to understand how people use these two shared resources, electricity on the one hand, and space on the freeway, space-time on the freeway, in the case of transportation. And the one thing we've seen because of the power of computing is this thing called disaggregation. So what does disaggregation mean? It means that when you have a smart meter on your house, if you were allowed to take a look, if the utility company was allowed to take a look, it is allowed to take a look at the consumption data that comes out of your smart meters, it is able to determine the pattern of usage of the data. And a theorem that one can prove is that if a high enough frequency of sampling, you can really extract very detailed information about the usage. For instance, if traditionally smart meters in the US are 10 minutes. There are some experimental utilities in Michigan which are doing 1 minute interval monitoring of smart meter data. Well, when you get down to if you can get down to, even 20 times a minute, which is sort of 1/3 of a hertz, you can really tell what appliances a person's using, the level of occupancy of a house, and if you get into a low enough frequency, high enough frequency, I should say, you can actually even tell what channels they're watching. And if this all sounds scary, I'm going to address that in a second. The same for cell phone towers. Just from people handing off calls as you drive on the freeway, the utilities can determine, really, to pretty good precision, people's driving habits, your source-destination pairs and the likely routes that you're likely to use to do this. And that's what disaggregation means, from looking at aggregate data to determine what individuals are doing. And why would you want to do that? Well, you'd want to do that because higher fidelity can lead to what is called demand response. That means that, if you're at a peak where it costs a lot to cater to very large peak demands because you've got to build new reactors, new power plants to do that. If, on the other hand, you could do some load balancing, it's called direct load control. That's what this acronym means. To be able to shave off the peaks, then that you can actually do this. You can ask people not to wash their clothes in the middle of a peak usage. So those are the kinds of things. There'd be advisory, people respond to them. There could be pricing signals, increasing the price of electricity so as to get them to do that. And that's why you would want to do this. Big question, privacy. It really is pretty darn invasive. You will all agree with me that it's pretty scary to have the utility determine the level of occupancy of a house. In fact, there was a celebrated case in Los Angeles. The district attorney found that the mafia was spoofing data coming from smart meters to determine the level of occupancy of homes so as to determine when to send teams of burglars to break in. So this is pretty scary stuff, right? And so the question is, what do we do? Utility versus privacy. Utility is a societal value. It's good for everybody. If you don't build more power plants, presumably your rates won't go up because you don't have to pay for them. But on the other hand, privacy is an individual value. It's not constitutionally guaranteed. I don't think privacy is absolute. I do think that when you think about privacy, when you go to a doctor, you're willing to reveal to a doctor all kinds of intimate facts about yourself in the expectation that you will get services from them. So people are willing to reveal private data if you could provide a monetary or you provide a utility for what you get in return for this. So we believe that we believe that privacy has a utility value associated with this and could be priced. So there are probably high privacy settings. There's now agreement even among legal scholars that privacy is not yes or no. It really is a question of being priced. In high privacy settings, low privacy settings are things that you could price for. So why not use these as part of integrating the user? Why not give the users contracts which say, if you agree to a high frequency sampling and we protect how the data is stored, et cetera, then we will offer you a lower price on the electricity. And so why are the economists getting Nobel Prizes for doing this? Right? This sounds like common sense. Because it isn't. If you try to do what I just said, it told the utilities, offer people who are willing to have high frequency data about their smart meter usage lower prices, and people who don't want to reveal their preferences get a higher price. What happens is that the resulting Nash equilibrium, which is the kind of equilibrium when you have multiple users associated with it, is actually one that results in bigger companies which actually don't want to reveal their usage, freeloading of ostensibly the smaller users who, in the expectation of getting lower prices, say, I'm going to give you lower frequencies. So the reasons that you really need to pay attention to theorems like this, and that's what this theorem's about, is that the Nash equilibrium in itself does not build in the societal values that are needed. And perhaps there needs to be a side payment to be able to build in a societal value on top of simply a Nash equilibrium. Because there's a colleague of mine called an economist, actually even a Michigan guy. He was the first high school dean here, actually, Hal Varian, who proved a wonderful theorem which said that if you let the Nash equilibrium continue, there's a big gap between the societal equilibrium, which is what is good for everybody, the sum of everybody's utility functions, and the Nash equilibrium, and it's sometimes called the price of anarchy. Anarchy is because if everybody does their own free choice, that's what's called anarchy, I guess. It's not real anarchy. You worry about a Berkeley guy talking about anarchy, I'm sure. But I think that that particular fact, and he, by the way, now is the chief economist at Google, and his story is really about how do you bridge the gap between the societal optimum and the individual Nash equilibria. And that's what all of this work is about how do you do this while building in societal values. And this is very, very interesting work. It's questions which include, do you really believe that humans are rational? Are they actually utility maximizers? And that's where the behavioral economists come in and they say, there's two in particular called Kahneman and Tversky, who said that in fact it isn't the utility function. We in our human experience tend to be conservative. We overvalue risk. We're very risk averse as human beings in general, and so you got to build this in to our behavioral models. And actually, the person who got the Nobel Prize announced a few days ago was a collaborator of Kahneman, one of these Kahneman and Tversky, who actually sort of took up on this theme. So it's all very, very interesting, and it's a place where sort of psychology, decision-making, that's where behavioral psychology, behavioral economics lives, economics, and of course the Internet of Things and cloud computing. And so even though data is emerging as a commodity, the social implications are amazing. So now let me lead you through another set of applications, this time in transportation. And I want to attribute them to my colleague, Alex Bayen, who runs the Institute for Transportation Studies. So he started pushing this idea of sending people routing information on their cell phones, mobile millennium, a little before, and he did it with Nokia long before Google Maps and Waze and all that came along. And this is what happened, and the fundamental premise of routing services are that every user gives people the shortest path, and some of them follow the recommendations, and et cetera, et cetera. The routing does not, and we all have experiences with using these routing services. You know, the forecasts of the network depend on the traffic that is there today. By the time you get there, maybe the traffic would be different. It doesn't take into account what people do, whether they follow the instructions or not. And finally, it doesn't take into account when there are multiple competitors in the same market, what it does. And here's what happens as a result. Just to tell you why this is, I'm going to just lead you through a number of news articles. Initially, people thought the application helped. And here are all the enthusiasm about how this is just going to be wonderful. Then people started noticing that drivers are being pushed into neighboring streets. New traffic apps are making residential streets, quiet residential streets, bad. Then locals are upset because they say this damn Google Waze is what's making my neighborhood crowded. And then they destroy their streets. LA traffic is the same guys who applauded it, including the mayors, are up in arms. And traffic jam uproar. This is a little bit of Southern California story. It's all over the country. It just so happens that's where I got on newspaper headlines. The citizens start to arrest. They start putting detour signs, homemade detour signs, and they take steps to keep commuters off freeways. Neighbors are fighting off traffic, and then they start putting in speed bumps. This is all in response to the smartphone apps to try to discourage people from getting off. And of course, there's no real policy to help elected officials. And by the way, the lawsuits are also beginning. So in Israel, for instance, the first lawsuit was in Israel for somebody that sent a driver inadvertently through a settlement when he was trying to find an optimal way to go from one place to another, and he got into trouble from this. So so there's a little more of the highlight. This was the. So what is the situation? I do think that we have a responsibility here to build a society that we want. And I do think this question about who is responsible, there is a trade-off between letting people get to their destinations in the fastest possible way and the wear and tear. We've built freeways to take a lot of wear and tear, but maybe we haven't made our neighborhood streets to take the kind of wear and tear that happens. Who pays for the extra congestion if these bypass roads become a problem? And I don't know if you've noticed this other phenomenon where Google Maps will tell you there's a blockage on the road, and it tells you to take a deviation, and everybody takes this deviation. And by the time you take the deviation and the traffic, if the original obstacle accident got cleared, in fact, there's a new traffic jam, and the original. And I've certainly had a lot of experiences with this when I've followed the instructions, and that's because nobody actually models who heeds the advice. And if Google Maps is doing something different from one of the Apple applications and so on, who is to intermediate between all of these? These are real issues. They're technical issues, but they're societal issues. And they involve an understanding of how we do it. So that's why, it's too trite to say that this is big data analytics, machine learning, IoT. There's a huge social component to these. Even though I really think that what's going to happen here is this convergence between IoT, cloud computing, data analytics, and AI. And we refer to this as really a digital transformation of societal systems. I've given you two exemplars. This is from this paper that we've written. And again, this is now McKinsey's predictions about what the impact's likely to be. It's just off the charts. And amazingly, unlike in 1973, by the way, there was a Harvard psychologist called William Bell who wrote something called The Forthcoming IT Revolution. And he wrote this at a time when really there were, there were no PCs, there were no microprocessors, and he foresaw a time when things would change. It took 40 years, and that was probably because this was much more a bottom-up. People had to convince their IT departments, their CIOs, and then it got up into the boardroom. This time around, what's different is that the CEOs are pushing for this. The CEO of GE, Jeff Immelt, was the one who coined this term industrial internet. And so on. Every one of these has support from the top. So what's the agenda for us? The agenda for us is to really think about how we architect the societal scale cyber-physical systems. And there's going to be new service models. There's certainly new service models coming. I didn't even talk about ride sharing and autonomy and all of that. So that's yet another set of things. But I do think, and I'm going to say a little bit about UAVs. Let me sort of lead you through yet another kind of application. This is about how would this be useful to really think about supply and demand. So every country has a diagram like this. This is called a Tokyo subway diagram. These are the sources of generation, and those are the sources of consumption, and the size of these bars tells you how much is. But on the demand side, there's almost always just these three big consumer items besides wastage, which is actually the gray bar on top. That's heat and transmission losses and all of that. So buildings, industry, and transportation. In the US, the mix is almost identical. It's about, industry is a little more, it's 40%, but the other two are about 30 and 30. That's the number. In other places, for instance, in Singapore, it's a little less on transportation, a little bit more on industry, and so on and so forth. But really, if you were to think about a roadmap in the style of a semiconductor roadmap for cutting down on all of these, because you have an IoT, et cetera, infrastructure for the demand side, you'd come up with really thinking about how you would do energy conservation on the building piece of it. This is Arun Majumdar's, my colleague when he was at DOE, writing down how he thought that a building system need to be viewed as an operating system, a cyber-physical operating system, and how you then use multiple sensors in order to be able to really reduce the energy consumption. The joke about buildings is they'll have one thermostat which will be close to the door. It measures the temperature of the corridor, and then it makes everybody either too hot or too cold. Whereas in fact, you have lots of sensors. The average modern building maroons a lot of HVAC data. It in fact has louvers that could be individually operated, which are not individually operated. And so the questions about how to do this, and lighting and so on and so forth. So why not try to do this? If you sort of keep going like this, you really would be able to start thinking about things like urban mobility differently, air transport differently, the electrical grid differently, and for instance, even this notion of thinking about what you do with drones on urban airspace is something to think about. By the way, when I was a kid growing up, we all used to read Popular Mechanics about flying cars, and and that was 40 years ago, and we thought the day would never come. It's here. People are actually making electric flying cars. They are. It's some of them are even flying, but the others are getting close. But the question of really how do we use urban airspaces? And it's not a surprise that in the developing world, especially in the developing world, the need for the third dimension in urban transportation is huge. The countries with the largest helicopter fleets, Mark, you might enjoy this, the three cities with the largest helicopter fleets are Sao Paulo, Rio. He's part-time in Brazil, that's why I'm telling him this. So, Sao Paulo, Rio, and Jakarta. And so, this is not like Jetsons. It really is a solution of electric mobility, but you've got to plan an infrastructure. And electric, it has to be quiet. It shouldn't add extra pollution. You have to house the airspace. It's not just Jeff Bezos wanting to drop your Amazon packet using a drone. This is really about transporting you from location A to location B. So all of this, the kind of technology we're talking about, how do you price it? I think all of this is really what's at stake here. This is Claire, this is my wife, in full disclosure, also my colleague, talking about how she wants to structure jetways above the Bay Area for air traffic. UTM, ATM is air traffic management, and UTM is unmanned air traffic management, to be able to avoid corridors. In fact, it could be like fiber optic cable, it might just follow right-of-way passages on the roads and rail tracks. And that could be the first place you start, making sure that they don't crash onto the roads. And all of that safety stuff. In fact, amazingly, one of the leaders in this is a Slovakian company. Slovakia has a rich tradition of making cars as well. And for usually all the automakers, perhaps GM also makes them in Slovakia, but they have an electric car project, as Uber and Airbus is thinking about. There's a lot of them that is moving along. But I think how we build the infrastructure to take advantage of this is interesting. I want to conclude, and I know I want to do two more things. The first thing is about humans and robots. And the theme of these things, there's one theme in the talk, it is that yes, it's technology. It's the newest, most wonderful technology. But there's a huge social science component. In this case, it was econ. Now I want to sort of tell you about human utilization and psychology, cognitive psychology, and how it is that it's important to really think about human-computer interaction really with the kind of rigor that we are used to, but in a way that really makes us understand the participation. And the last thing I want to say is something that I'm sure would be close to Kathleen's heart here, would be about technologies for poverty alleviation. So I'll go through this, and I promise I'll end in time. So just in case you have a sinking feeling about seeing more slides when you're exhausted. So I think what's changed in robotics is really the sense. We began saying that robots were for doing tasks that were dull, dirty, and dangerous, and by and large, we want to get humans out of the loop and let the robots do their work. What's changed is that we actually want robots working shoulder to shoulder with you, doing tasks where, which you do, but you perhaps don't want to do all the time. You want robots to be caregivers. That's a big part of this. One of the earliest commercial humanoids I was saying, Conwell, was Sharp makes a cell phone-like humanoid called Robohon, which was really to entertain people who live by themselves and also to call the cab. So Robohon was bought by Foxconn. Foxconn, as you know, is, I think, and now everybody knows about Foxconn going to Wisconsin, but Foxconn is going to get into this business of really thinking about humanoids. So how do you model humans working with robots in some guaranteed fashion? And more generally, when you think about AI systems, how can you guarantee what they do? And this sounds like an oxymoron because, a learning system by definition does something different than what it was designed to do. But nonetheless, you do want somebody you trust. You want to have a partner who actually evolves in response to you. So how do you come up with a theory for thinking about what are called provably correct AI or provably correct human-robot systems? And the general story is, let me skip through this, is that it's a big resurgence in AI in terms of thinking about learning. So I'm sure all of you have heard about the incredible successes of deep learning, deep residual learning. But the question is, when do they work and when don't they work? What happens when an auto company, whose name I won't tell you, spontaneously reboots your car? And how does it change when you interact with it? So these are all big questions for being able to think about what it means to model humans interacting with automation. So let me lead you through And this is my colleague, my classmate, Eric Schmidt, talking about one of the biggest challenges are that blending them in with humans, and humans don't behave by the book. It's true. And in fact, one of the things that Waymo suffers from is somebody going to try to confuse it. And so we began a project where we were actually trying to use inverse reinforcement learning techniques to learn about driver intent, to be able to understand what would happen when human driving interacted with an automated car. This is a student of mine who just finished, called Dorsa. She's now on the faculty at Stanford. And what she found was that, so the white car is a robotic car, and the orange car is a human-driven, the white car is a human-driven car, and the orange car is a robotic car. There's two things that one can do. Oh, it's spontaneously moving along, okay. But, the story is if it's an aggressive driver, then you let the aggressive driver go before crossing over, whereas if it's a friendly driver, it will let you cut in front of them. You do this, and how do you figure out whether it's a friendly driver or a distracted driver, and how do you then model this? And the amazing thing is that you can actually, by observing the driver, of course this was done on simulations, not on the real cars, be able to come up with models of whether the human driver is distracted, whether it's aggressive, not aggressive, and the actions that you would do in order to do this. And her pièce de résistance was really to think about what you do with these kinds of schemes when it came time to have a robotic car and a human car at an intersection. And this quite often can result in a deadlock, and it's called the dining philosopher's deadlock, and so on and so forth. And amazingly, when she applied this, she found that the robotic car actually backed up in order to sort of tell the other person, please go, tell the human driver, go ahead. And so, I think by tuning these things, you can actually start coming up with models of how you can make these things interact with humans and come up with predictable models of how this thing would verify. And what I've left out of this is that there's sort of probabilistic reasoning that goes into the kinds of behavior that you would expect of this person that gives you some confidence, not to mention that once you have these models, that's when the auto companies can get it certified. People can buy insurance. Why you need these guarantees to buy insurance? Because the insurers need to know risk, and the cost of premium is the cost of probability of an accident times the average cost of an accident. That's they also charge a premium for making a profit, but modulo that's the theory of insurance. But so in order to be able to do this, these are the kinds of guarantees that you can come up with, and come up with these different models. Here's an example of somebody who was texting to play the role of a distracted driver, and so on. And so all of this, and again, in the interest of staying on time, I won't go through the greater details of this, but all of this is creating a field called safe AI. And what does safe AI mean? It means that learning happens at a time when you can guarantee that you don't run into things. You're safe. Actually, safe has a technical definition as well in terms of, in this language called temporal logic. But it also says that when you are safe, when you are in this safe learning envelope, you can in fact apply learning in order to be able to learn characteristics. And again, there's a very, very rich literature about the interaction between learning control, adaptive control, and this latest rebirth of neural networks, which is deep networks, of deep residual networks, which actually results in being able to come up with proofs of when these learning systems work. There are numerous learning control faculty in this audience, I know, and I would really encourage you to go back and start thinking about the connections between that and these deep neural networks. This is the third incarnation of neural networks. But I think that it really is possible to think about what we are calling assured autonomy. In this particular piece, let me just talk to you a little bit about humans interacting with the robots. And I want to leave you with what looks like a toy example. This is a little experiment with my colleague Anka Dragan about how there's two robots. This is the Child's BB-8 and one of these Pioneer robots, and they're trying to solve a traveling salesman problem. So traveling salesman, you traverse these 5 obstacles using minimum length. And the problem is that if you are given the first 2, it's ambiguous as to where you go next unless you've done the calculation. Okay, and if you ask human beings to do this, this is the probability of what path they will choose as the next state given the first 2 states. So what we tried to do, and in fact, this is the optimal algorithm if you weren't given the order. But what t-predictable planning says is given the first 2 states, how do you, when there are accidents in automation, quite often the transportation safety boards or other safety boards will say, the human did not understand the automation, or the automation did not understand what the human was trying to do, and that's classified as operator error, and that's the end of the story. So why not have a situation where the robot is explaining to the human predictably what it is going to try to do? So here's an example of the difference between robotic and t-predictable planning. T is the number of initial steps that you're given, and t was equal to 2. The first 2 steps, the first step was given, and it was asked to. So this, I'm going to play the movies associated with this. The first one is, this BB-8 is going to guide this big robot based on where it thinks it should go, and this is operated by Roy, who's up here. Whereas the t-predictable one, it is, it's guiding it, but it has, this one is following the robotic optimal algorithm, whereas here, it's following the t-predictable one, which is not as optimal. And so if one plays these, this is the other one, it gets confused as to what the human doesn't know which is optimal, so after it's done the first 2 steps, the human's trying to get it to go up there. But in fact, the optimal one went there, so it gets run over by this thing, and then those are the kinds of comments. And these are the psychophysics that goes along with having multiple subjects do it and evaluate it for the kinds of metrics that you do out of these. So, I think that this whole idea of getting humans and robots to work together is a very, very rich area. The connection with arts, by the way, is that this new set of technologies around augmented reality, virtual reality, all the cell phone makers are now making AR devices. HTC currently is an example that makes me think of Vive. It's off and running in order to do this. Oculus, Facebook, Google Glasses, everybody's making these devices. And the question is, why not use them to really augment cognition in ways to make it better? And amazingly, the lead adopters of this are going to be in the performance arts. Because really, it's going to change how you view performance. This is like super titles at an opera on steroids. It's really super titles to the power n. That's really what this is. And that's why I think it's very, very important. And of course, game playing is another place. That's certainly the first place it's being used. So these are the places that you'll be able to actually refine these techniques. And I think it's the NBT. In Silicon Valley, everybody's got to come up every day with what the next big thing's going to be. I really, to make fun of ourselves, I have to say that's why I put this in as that. And related to this is really the human internet. So let me end by just telling you a little bit about poverty alleviation. The other thing, we sit here at American University, and we are really, I know a lot of you are students here. I must say, after 20 years, I really see idealism back in the student body. And I think all of you, I feel, care a lot more about America's place in the world and thinking about poverty alleviation. And the kinds of technologies that you're talking about just are amazing in low resource settings. And they actually involve really this wonderful blend of technology, entrepreneurship, and design to think about this. So here at Berkeley, we've put together a program run by a mechanical engineer called Alice Agagino, who some of you know from the design community, who is really thinking about development engineering. What is development engineering? It's the engineering of development. That's really poverty alleviation. Poverty engineering, development engineering in a style which I certainly was first exposed to through the work of C.K. Prahlad here in the Ross School. He was a big hero of mine, I have to say. But it was, why can't we use admittedly really super capitalist techniques, which is what these are, to really think about poverty alleviation? And here are some examples. Now, we assume here that everybody has cell phone towers. In a lot of places, people don't have cell phone towers because cell phone providers don't think they'd make enough revenue by putting up the towers. This is a place in Indonesia, but on the other hand, in the United States, there are lots of places, especially in the great open spaces of the West, where there's no cell phone coverage. Quite often in American Indian reservations, and as a result, banking. There's a big, the big social costs associated with not having connectivity nowadays to do this. And so the question is, why not have store and forward devices? So local cell phone networks. Why not set up your own cell phone networks? And that got put together as after tests, both in a lot of places, both in the Philippines and Indonesia. Also, there's a lot of money transfers, and those need to be done on a large part of the economy is around these money transfers. And what happens is, the students love this, put this together, and what I didn't put is the spin-out was acquired by Facebook. Of course, Facebook really views providing services like Facebook, on top of the money transfers. And by the way, the group that actually didn't care for it was Western Union, because it sort of got in the way of their commissions to transfer money. Other examples. This is a microscope on a cell phone. Microscope on a cell phone. This is Dan Fletcher, another colleague of mine. And what difference did that make? I think, and this is where I'm looking straight at Kathleen there in the row back there. I mean, this is about really providing microscopy to places which don't have hospitals, don't have clinics. And if you can make it easy to take samples, and in the old days you had to send it out on the web, but now there's more computing power on the cell phones themselves, so you don't even have to send it out so as to do this. And this got used for TB in Vietnam. This is Loa Loa, which is something which is like the river blindness in West Africa. And this is Thailand for detecting early retinal detachment. And those are the kinds of things that you can prevent. And these are big ticket items. They're all scalable. There are companies that can make money off it. Another one is called We Care Solar. It's about technology for providing portable power in delivery rooms in West Africa. And the idea, we've all been in the developing world, the power goes off at the most critical instant. And so the question, why not have a solar suitcase? This is Laura Stachel pushing this notion about it's a solar charging station. And we had this discussion about, is this cool technology or is it just sort of off-the-shelf technology? And the answer is it's somewhere in between, and it's all of the above. And when it comes time to monitor and to determine how effective it is, judging the effectiveness of these things needs all of this sort of data gathering mechanism, analyzing it, and then being able to suggest changes in order to do this. Another one in India is for arsenic removal. By the way, here's an example of a technology that we developed for use in West Bengal and Bangladesh. But as we were doing this, we found out that in the Central Valley of California, Merced and so on and so forth, there is a huge amount of arsenic in the groundwater. And in fact, a lot of the issues, the public health issues associated with drinking contaminated water were present right in our backyard. And Arun Sareen, who's one of my advisory board, said, it's a question of how these technologies boomerang back. And so as you start working on technology in low resource settings, this kind of technology really absolutely, it's a very rich blend. On the one hand, it'll be extremely advanced in other places. On the other hand, it'll be very common-sensy on the other hand. But in terms of making a real impact on the world, and I know, Mr. Korybalski, you support these projects in the MECI department, so I'm just plugging your investment in these projects. So I think that really what we need to do here is, because of this idealistic generation, is to really challenge our students. And the question of, can we use price competitions as part of the educational paradigm? And that, I think, is something that's a work in progress. We started a price competition which we're evaluating called Big Ideas. There's an on-ramp to innovation that follows the big ideas, prize winners, and so on and so forth. And the question is that a good part of the educational experience? Is an important one. And I will conclude now with my a couple of slides. The NRC talked about, how do industry and companies collaborate to do this? And the short answer is that, it takes a long time. And these diagrams are called tire track diagrams. These were done in 1993, so some billion-dollar payoffs. And the arrows represent, the red ones are the big industry, the blue ones are the universities, and the green ones are big companies. They change from dashed lines to green lines when the revenue becomes $1 billion. Now, this old model of translation, somebody does exalted science, somebody else does the technological development, a third person does the entrepreneurship and makes money. Nothing is further from the truth. Look at these tire tracks. There's a lot of motion back and forth. And one does need to be patient. On the other hand, I do think we have to create ecosystems that allow faculty, students, to move back and forth from industry to startups, the middle stuff of the startups and the big companies. And, so that, I think, creation of this ecosystem is really important. The NRC loved their tire tracks so much that they graduated a couple of years ago to do a $10 billion economic impact story. And they produced this tire tracks, except the tire tracks are now vertical. They added these new sectors. And the story is roughly the same. I don't think there's anything new that came up with it. So I'll end with what I think we need to do, not just at Berkeley, but at Berkeley I think I'm going to try to build this institute, this hub called Inventing the Future, because the future is just too important to let happen to us. I don't think we want to be in a future where some set of robots sends us packing off to Mars, which is something that you might read in the papers. I think that, we don't want the world to become the way you saw in terms of those, the apps around Google Maps and so on and so forth. We really do need to play a role in providing this entrepreneurship, technology, design, with social impact built in on all of these kinds of grand challenge problems, while really keeping up with the glamour technologies du jour. Today's glamour technologies are different from yesterday's, and they will be different tomorrow. But what is constant is our need to invent the future, and our need to sort of invent it with the technology as a given to employ to enhance the human condition, which I think we all deeply believe it can do, while sort of also preserving society to be the way we want it to be. It includes retraining people. There's jobs, there's all kinds of stories, which were, I think recently Rod Brooks debunked one about robots taking away jobs. But having said that, I do think we have part of this responsibility as a continuing education responsibility for our students after they've graduated to keep them current in whatever the glamour technologies du jour is. So that's sort of a summary of this. And at Berkeley, we're going to try to build a building, which we're going to call Inventing the Future, which will have, I think, I have to say, Gigi Brown is a fantastic building. And I got a lot of ideas from looking at the spaces in there, which I think will be in the next incarnation of this set of slides. And I'll attribute them, don't worry. So thank you very much for your attention. And if you want me to take questions, I can. And if not, there's a reception. Right?